Welcome to this explainer. Today we're taking a radically different approach to mastering the Cambridge physics syllabus, specifically code 0625. I like to call this strategy the paleontologist. Think about it. When you look at a complex exam question on, say, electromagnetic forces, you can't just scratch the surface. You have to carefully dig through the fossil layers, uncover the specific question parts, and reconstruct the full, perfect answer. Today, we're going to demystify one of the most incredible relationships in the entire universe, the hidden link between electricity, magnetism, and physical motion. But we're doing it by looking at two typical students. First, there's Alex. Alex is the kind of student who overloads every answer with raw physics facts, but includes zero actual analysis. Then we have Sam. Sam always rushes, completely missing the crucial command word requirements in the prompt. We're going to look at their flawed answers, break out the red pen, and show you exactly how to secure those top marks. So if you've ever wondered how electric cars drive or how to write an exam answer that examiners absolutely love, you're in the exact right place. Let's dive into this.
We are going to build our understanding today like a highly strategic mechanical puzzle. We'll start by digging into invisible magnetic fields, then see electromagnets in action, explore the motor effect, learn how to flawlessly apply Fleming's left-hand rule on paper, and finally, build an electric motor. Every single one of these 5 steps represents a common pitfall in past papers, and we are going to conquer all of them.
All right, let's start with section 1, invisible magnetic fields. We have to begin with the absolute basics of what happens when electricity begins to flow, because this is where we see our first major exam trap.
So, look at this classic exam question. What happens when an electric current flows through a wire? You might just think it powers a light bulb or charges your phone. Our student Alex looks at this and immediately starts writing a massive paragraph about electron drift velocity and battery voltage. Factually true? Sure, but it scores 0 marks. Why? Because the core physics concept being tested here is that every single electric current creates an invisible magnetic field around it. You can't see it, but it's there, wrapping around the conductor. When you're answering this, you have to hit the exact assessment objective the examiner is looking for, which is identifying that electromagnetic relationship directly.
Now, to actually visualize that invisible field and grab those exclamation marks, I want you to literally raise your right hand right now. We're going to apply the right-hand grip rule shown on screen. Imagine gripping the wire so that your thumb points in the exact direction the conventional current is flowing. The curve of your fingers perfectly maps the shape and direction of the circular magnetic field lines around that straight wire. If the current reverses, your thumb points the other way, and the field lines reverse direction too. If you describe this exact physical orientation in your answer, you are instantly demonstrating high-level comprehension to the examiner. But what if that single wire isn't strong enough? If we want to make that magnetic field stronger, we just wind the wire into a coil. In physics, we call this a solenoid. Wrapping the wire this way is a brilliant method for concentrating the magnetic field into a much tighter, more powerful area. Now, when Sam gets a question asking to define a solenoid and explain its benefit, Sam usually just writes a coiled wire. That loses marks. You need to go further. You need to use our PEL framework: point, evidence, explanation, and link. Your point is that it's a coiled wire. Your explanation is that this shape actively concentrates the magnetic field, making it significantly stronger than a straight wire. Let's compare the two directly, because comparison questions are incredibly common. While a straight wire has circular field lines that just get further apart and weaker the further away you get, a solenoid is entirely different. Inside the coil of a solenoid, the field lines run perfectly parallel to each other and are very close together. This proves the field is strong and uniform. In fact, the overall field pattern of a solenoid looks and acts exactly like a strong permanent bar magnet, with a north pole at one end and a south pole at the other. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Moving right along to Section 2, Electromagnetism in Action. Now that we know how to create our own electromagnet, how do we actually analyze its use in real-world exam scenarios? This is where the application marks live.
Look at this brilliant diagram of a car ignition. When a driver turns the key, they are only using a small, safe current. But starting a car engine requires a massive surge of power from the battery to the starter motor. We absolutely do not want thick, dangerous cables carrying hundreds of amps running right up into your dashboard. Instead, we use that small dashboard current to operate a relay, an electromagnetic switch that safely turns on the massive current circuit located deep in the engine compartment. When Sam gets this question, Sam just writes, "The magnet turns the motor on." Again, rushing and missing the command word, explain. Let's transform that rushed answer using our physics success blueprint. We need a clear step-by-step breakdown. The crucial point is how this relay sequence works in 4 exact steps. First, you turn the key, and the small current flows through the electromagnet coil. Second, this magnetizes the core and attracts a pivoting piece of iron called an armature. Third, as the armature moves, it physically pushes 2 contacts together. Finally, those closed contacts complete the completely separate, high-power secondary circuit firing up the starter motor. By clearly sequencing your answer like this, you turn red pen marks into green check marks. It's a completely safe, ingenious use of an invisible field and a perfect 4-mark answer. Now we're getting to the really fun parts, both in physics and in our exam strategy. Section 3, the motor effect. We know electricity creates a magnetic field. But what happens if we take that electrically generated magnetic field and force it to interact with a separate, permanent magnetic field? Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. The answer to that interaction is movement. This creates a physical, pushing force known fundamentally as the motor effect. By simply combining a current-carrying wire with a magnetic field, provided they aren't parallel, we generate a physical force exerted right onto the wire itself. This definition right here is a prime target for a 2-mark recall question. Don't overcomplicate it like Alex does, just state the specific conditions: current flowing, in a magnetic field, not parallel. Bam, full marks. All right, it's time for our first interactive workshop challenge. I call this the data scan. You have 60 seconds in an exam to look at a complex visual like this catapult field experiment and extract the core trend. Notice the thin aluminum strip placed between 2 very strong permanent magnets. The moment a current is passed through that metal strip, its newly created magnetic field clashes with the permanent magnet's field. What's the result? The aluminum strip is violently pushed downwards by an invisible force. And if you were to reverse the current or flip the magnets upside down, the strip would be forced upwards instead. Identifying that reversal relationship is exactly what the examiner is testing here. Which brings us perfectly to Section 4, Fleming's left-hand rule. If we want to build precise machines and write precise exam answers, we need to be able to predict exactly which way that physical movement will happen without having to guess. This is where we run into Challenge 2, finding the flaw. Look at this diagram. For the right-hand grip rule earlier, we used our right hand. But so many students, just like our rushing Sam, try to use their right hand for this motor effect calculation and lose every single mark. Hold out your left hand. Arrange your thumb, your first finger, and your second finger so they are all at perfect right angles to each other, exactly like the diagram on screen. It might feel a bit like a strange hand cramp at first, but this specific posture is the absolute key to unlocking electric motion questions. This is Fleming's left-hand rule, and it perfectly predicts the direction of force. Here's the trick to remembering it for your speed writing challenge. Your first finger represents the magnetic field, always pointing from north to south. Your second finger represents the current. Once you line those 2 with your system, your thumb will automatically point in the direction of the resulting motion, or force. It's a foolproof way to calculate the motor effect in 3 dimensions. If you have 30 seconds to write a perfect Peel paragraph, your point is the rule itself. Your evidence is the finger alignment. Your explanation is how the fields interact, and your link is stating the final direction of motion. Let's move to our final section and see how this builds into something amazing. Section 5, Building Electric Motors. Now for the best part. Let's snap all these physics principles and all our exam strategies together to build some machines and grab those final marks. First up, we have the loudspeaker. It uses the exact same motor effect we just discussed. A varying electrical signal, like your favorite song, is passed through a coil of wires situated inside a cylindrical permanent magnet. Because the current is constantly changing its magnitude and direction, the resulting magnetic force on the coil constantly changes too. This forces the attached paper cone to rapidly vibrate back and forth, pushing the air and creating the sound waves you hear. When an examiner asks you to explain a loudspeaker, they are checking to see if you mention that specifically varying alternating current. If you just say current makes it move, you are acting like Alex, missing the crucial analytical layer.
But what if we want continuous spinning, turning motion? In a direct current electric motor, we place a rectangular coil of wire horizontally inside a magnetic field. Look closely at the flow of electricity here. The current flows up the right side of the coil and down the left side. Applying Fleming's left-hand rule, which we just mastered, this means the right wire is pushed upwards and the left wire is pushed downwards. These opposite parallel forces create a massive turning effect, making the whole coil spin. This is a classic 6-mark explanation question.
But there is a massive trap here. When the coil reaches a vertical position, the forces no longer provide a turning effect, and the motor would just get stuck. The crucial point here, the absolute genius of the motor, and the exact detail examiners hunt for, is the commutator. The split ring commutator is a spinning connection ring that cleverly reverses the electrical connections to the coil every single half turn. Just as the coil flips over, the current flips too. This ensures the forces always push in the same rotational direction, keeping the motor turning smoothly and endlessly. If you forget to mention the commutator reversing the current, you kiss your top grade goodbye.
Now, a small model motor is great, but to build powerful electric vehicles or heavy industrial pumps, we need more turning force. We can easily crank up the power of our motor in 3 straightforward ways. We increase the number of turns of wire in the coil, we pump more electrical current through it, or we use much stronger permanent magnets. And just like increasing the power of a motor, we have 3 rules that guarantee top marks for your exam system. 1. Command word decoding. 2. Peel framework application. And 3. A strict time management matrix.
We've successfully turned invisible electrons and magnetic fields into powerful, useful mechanical motion today, and we've decoded the examiner's mindset. Which leaves me with one final, slightly provocative thought to ponder. We just learned that pumping electricity into a coil surrounded by magnets creates physical motion. But physics loves perfect symmetry. What do you think happens if we do the exact opposite? What if we manually turn a crank to physically spin that wire coil inside the magnetic field? Could physical motion actually create electricity? That's electromagnetic induction, and it's a story for our next explainer. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to Ace the Exams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.